Hello everyone. In this video, what we'd like to talk about is the relationship between the unit tangent vector, the unit normal vector, and the acceleration vector for an object's movement. So we're going to learn how to calculate what's called the tangential and normal components of acceleration. We're going to figure out what those numbers are telling us about the object's movement. And then we're going to figure out an alternative sort of shortcut method of finding the unit normal vector, which relies upon the tangent vector and the acceleration vector. Now, before we get started, there are a couple of observations that I feel the need to highlight, feel the need to bring to your attention in case you haven't seen or noticed them before. And the first observation that I would like to make is about the relationship between between a vector's length and the dot product of a vector with itself. So if you have a vector v, for example, suppose that v is written abstractly as vx, vy, and vz. If you dotted that vector with itself, then you would get vx times vx, the two x components multiplied together, vy times vy, the two y components multiplied, vz times vz, the two z components multiplied, and then you would add those results together, and that would be equal to the dot product of this vector with itself. Now compare that with what you get if you take the length of the vector v. The length of the vector v would be equal to exactly the same thing, except with a square root applied to the quantity. And as a result, the following property is satisfied. If you take a dot product of a vector with itself, then the result that you get will be equivalent to the squared length of the vector. And in particular, if your vector v happens to be a unit vector, if its length happens to be 1, then in that particular case, the dot product of a unit vector with itself will always be equal to 1 unit, that length of 1 quantity squared. The second observation that I would like to make is the following. I would like to highlight the fact that the unit tangent and the unit normal vectors are perpendicular to each other. Go back into the previous video, go back into the previous problem set, go back into your previous exercises, and you can confirm that in every single situation, the tangent vector and the normal vector form a right angle with one another. In particular, if you go back to those previous examples, and if you look at the geometric relationship between t and n, the tangent vector is just a scalar multiple of the velocity vector. So the tangent vector points in the direction that the object is moving. Where does the unit normal vector point? The unit normal vector points at a right angle to t, and the direction of the normal vector is in the direction that the object is turning. So if, for example, we had an object that was moving in a circle on a circular track, and if I froze a particular instant in time, say here, I can predict right away the direction of the tangent vector and the direction of the normal vector. The tangent vector is going to be tangent to the curve and in the direction of movement, so in this case, straight up. The normal vector is going to be perpendicular to that, so it could either point to the right or to the left. But in this case, the object is turning to the left, so that is the direction that the normal vector will point toward. Similarly, at any later time, the tangent vector will point to the left and the normal vector will point inward. Here, the tangent vector points down and the normal vector points inward. Here, the tangent vector points to the right and the normal vector points inward. Now that we've made those observations, let's return to the acceleration vector for an object's movement, and let's try to make some observations about the relationship between acceleration, the unit tangent vector, and the unit normal vector. To begin with, let's consider the following exercise. We have an object's position at time t, given by this helix. For this helix, let's try and figure out what is the rate of change of the object's speed. How is the object's speed changing over time? To that end, I'm going to start by finding the velocity of this object, calculating the first derivative, negative 6 sine of 2t, 6 cosine of 2t, and 5t becomes 5. And to find the speed, I'm going to take the magnitude of velocity, and applying the Pythagorean theorem to that, I can take this sine squared and this cosine squared and transform that into a 1, leaving me with this constant speed equal to 36 plus 25 square root. Because the speed is constant at all times, the rate of change must be 0. So in answer to this problem's question, part A, the rate of change of speed of this object is 0. Now let's compare the rate of change of speed to the object's acceleration. Part B, what is the magnitude of the acceleration vector? To that end, I'm going to go ahead and find the acceleration vector first, and then I'm going to find its length. So negative 12 cosine of 2t is our derivative of the velocity vector, negative 12 sine of 2t, and then the 5 in the velocity vector becomes 0. And if you calculate the magnitude of that, then once you apply the Pythagorean identity and the length formula, we find that the acceleration, after simplification, becomes the number 12. So what's going on here? In many cases, we intuitively think of acceleration as causing an object to speed up or to slow down. When we say in English something accelerates, in English, in colloquial English, that means that the object is beginning to move faster. But that intuition is in contradiction to what we have found in this example. In this particular case, the object's speed is not changing at all, and yet some kind of acceleration is happening because our object's acceleration vector is non-zero. It has a magnitude of 12 units. So if this acceleration is not causing the object's speed to change, what is this acceleration changing? The answer is that the acceleration represents the rate of change of the object's velocity. And velocity has two components to it. The velocity contains information about the object's speed, sure. And so acceleration has the potential to change the object's speed. However, velocity also contains information about the object's direction. And so acceleration also contains information about what's happening to that aspect of the object's movement. Acceleration captures both the changes to the object's speed and the changes to the object's direction. And that's what's happening in the previous example. The object's speed is not changing at all. The object is moving at a constant speed throughout its entire journey. However, because the object is following a helix-shaped path, the object is turning at all times. And so the unit 12 that we're getting for the magnitude of the acceleration, that entire magnitude is capturing how quickly this object is changing its direction. This dual nature of acceleration, its ability to capture how the speed is changing and how the direction is changing, is captured by what are called the tangential and normal components of acceleration. If you have an object with a position function given by r of t, and you have a unit tangent vector called capital T and a unit normal vector called capital N, then the acceleration vector can be written in terms of those two unit vectors. The acceleration vector will partly be made up of something that aligns with t, and it will partly be made up by something that aligns with the normal vector n. A is equal to this combination of the unit tangent and the unit normal vectors. Now this quantity a sub t, that is what is known as the tangential component of acceleration. It represents the portion of a, the amount of acceleration that aligns with the tangent vector. And the physical significance of this portion of the acceleration vector is that a sub t is the portion that captures how the object's speed is changing. It represents rate of change of speed. It is the other portion, a sub n, the portion of acceleration that aligns with the direction of turning. It is that portion that captures the rate of change of the object's direction. A sub n, the normal component of acceleration, captures the rate of change of direction. So scrolling back to the previous example, in this problem, the speed was constant and the rate of change of speed therefore was equal to 0. As a result, in the previous example, we would know for sure that a sub t was equal to nothing. A sub t is equal to nothing because a sub t is the rate of change of speed, and the speed was not changing at all in that example. Therefore, we would know that the acceleration vector was equal to a scalar multiple of the normal vector. So the entirety of the acceleration in that particular case, the entirety of acceleration would align with the unit normal vector. They would be parallel. Now, the tangential and normal components of acceleration, these two numbers, a sub t and a sub n, have a couple of interesting mathematical properties. And the first interesting property that we will be able to use is a very simple way of calculating these two numbers. The first property that we will use is that a sub t is equal to just the dot product of the acceleration vector with the tangent vector. And here is the reasoning for why this is true. We know that the acceleration can be split as a combination of some number times tangent plus some number times normal. Now I'm going to go into this equation and I'm going to apply the dot product with the tangent vector to both sides of this equation. So on the left side, I will get A dotted with the tangent vector, and on the right side, I will get this combination also dotted with the tangent vector. Now if I distribute that product on the right side, then that will become the same thing as this number AT times T dotted with itself plus this number AN times N dotted with T. Now because N and T are perpendicular, because they form a right angle, we know that their dot product will be 0. And by the observations made at the beginning of this video, we also know that the dot product of T with itself will just be equal to 1 because T is a unit vector. And therefore, after simplification, we find that the value of A sub T, the value of the tangential component, can be found as easily as taking A dotted with T. Now, a similar property holds for A sub n, and by similar reasoning, if you want the normal component, just take the dot product of the acceleration and the normal vector. However, this one is not going to be nearly as useful as this one. We're going to use this one the most. The second neat property of the relationship between the acceleration vector a sub t and a sub n is that the magnitude of acceleration can be found by just taking the square root of a sub t plus a sub n. So it's almost like the regular formula for the magnitude of a vector, except instead of taking the x component and the y component, we're taking the tangential component and the normal component, squaring those, adding them together, and finding the square root. This particular formula has a lot of applications in kinematics and engineering, for example. The third property that we will be interested in is the observation that if you take this relationship between A and its tangential part and its normal part, and you rearrange that slightly, then you find something interesting. You find that the normal vector n points in a parallel direction as this vector a minus a sub t times the tangent vector. Now, I'm going to give this to you as a fact. We're not going to explain why this is. We don't have quite the time for it in this class. A sub n is always going to be a positive number. There will always be an alignment between the direction of the acceleration vector and the direction of the normal vector. And the consequence of that fact is that the normal vector and a minus at times the tangent vector point in the same direction. Now, to show why this last property is really useful, and to show why it's especially useful in combination with property number 1, let's do a quick exercise. What I would like to show you is how these properties can be used in many situations to simplify the calculation of the unit normal vector. Consider, for example, the following exercise. We have an object moving with a position function given by this expression, e to the t root 2 times t times e to the minus t. In part C, we would like to find the unit normal vector at time t equals 0. And we recall from yesterday's video that the standard process for calculating this quantity is quite arduous. I propose that we can find the unit normal vector in this problem by a process that's not nearly as complicated. I claim that we can use properties number 3 and property number 1 to calculate the unit normal vector much more easily. To begin with, I'm going to find the acceleration vector at time 0. So finding velocity first, finding v as a function of time, we have e to the t root 2 negative e to the minus t. And then I can find the acceleration by taking the second derivative. Acceleration at time t is e to the t root 2 and e to the minus t. At time 0 in particular, our acceleration vector is e to the 0. Excuse me, this y component would vanish. The derivative of root 2 would be nothing. So that will just become 0, and e to the minus t at time 0 would be 1 as well. Let's also find the unit tangent vector at time 0. The unit tangent vector can be found by taking the regular tangent vector at time 0, which would be equal to e to the 0, which is 1, root 2, and negative e to the 0, which is negative 1. Find the length of that tangent vector, which looks like root 4, which is 2, and then divide the velocity vector by its length. That'll give us unit tangent. Next up, our mission is to calculate the unit normal vector at time t equals 0. But one of the things that is really interesting about the unit normal vector is that it points in the same direction as acceleration, take away this tangential part. So what I'm going to do is I'm going to actually work on trying to find this vector here, acceleration, take away tangential part. And then all I'm going to do is modify that vector to turn it into a unit vector, and that will be n. Now working on this expression here in the gold box, I already know the value of a, I already know the value of t, but what I do not know at this time is a sub t. And a sub t is equal to, here, a sub t can be found as simply as taking the acceleration and dotting it with the tangent vector. So to do that, so getting that quantity first, a sub t, I will find the acceleration vector dotted with the tangent vector. Our acceleration at the given time was 101. Our tangent vector at the given time was given by this quantity. And if you take the dot product, we find that the tangential component is equal to 0. So, because a sub t is equal to 0, this acceleration vector must not have any tangential component. This acceleration vector must not alter the speed of the object at all. The acceleration vector must point in the same direction as n. So n must be equal to this vector a divided by its length. The vector a divided out by its length will be a unit vector pointing in the same direction as a, and therefore it will be equal to our unit normal. And so with a little bit of arithmetic, you can find that the normal vector would be 1 over root 2, 0, and 1 over root 2. So in summary, a nice easy way to calculate the unit normal vector without having to do a bunch of excessive derivatives and really complicated derivatives. Step number 1, find the acceleration vector. Step number 2, find the unit tangent vector. Step number 3, find the tangential component of acceleration by dotting the acceleration with the tangent vector. Step number 4, calculate this quantity, a take away the tangential component times t, and then the result of that calculation will point in the same direction as your unit vector. So take the result of that calculation and divide out the length. And once you have done that, the result will be the unit normal vector. The unit normal vector can be found by taking a minus a sub t times t and dividing out the length of that quantity. It's really nice when a sub t is equal to 0. It simplifies very nicely. But even if a sub t is equal to some other number, you can still find the unit normal using this overall method. Okay. Finally, find the tangential and normal components of acceleration. We have already found that a sub t was equal to 0, so all that remains is to find a sub n. And at this point, there are a couple of different ways to go about this. Method number 1 is to use a similar approach to the one that we used to find the tangential component. And that's to take the dot product of the acceleration vector with the normal vector. Now the acceleration was equal to 1, 0, 1. The normal vector was equal to 1 over root 2, comma, 0, comma, 1 over root 2. And if I calculate the dot product between those two quantities, we get 2 over root 2, or in other words, just root 2. That would be the normal component of acceleration. An alternative method that could also be used to find the normal component of acceleration at this point is to use the fact that the magnitude of the acceleration vector is equal to the square root of a sub t squared plus a sub n squared. In this particular problem, the magnitude of our acceleration vector is equal to the magnitude of 1, 0, 1, which is equal to the number square root 2. On the far side of the equation, a sub t we found was 0, and so after some simplification, the quantity on the right side would simplify just to a sub n. So this would be an alternative way, using another one of our properties, to find that the normal component of acceleration is square root 2. So this particular acceleration is not causing the object's speed to change at all, but the rate of change of direction would have a magnitude of root 2.